Oh, yeah. You want to see a demonstration? No, that's very.
That's what how many years ago?
It's like.
Me and Ananda were in she said she was gonna give us
You're not supposed to be That's nice. Honestly, it's like once you get into a flow, it's very good. I'm already done. Yeah. Thinking of what's next. Like I found there's still no way. Yeah, I'm experimenting stuff.
All right, so getting ready to wrap up the week. I don't think there's any new announcements. That's the normal stuff. So we have today's class and then we have Wednesday and then we're done. So Wednesday, you've got your formal report due. So please bring in that at 11. And at the same time, I will return to you assignment 4, which I've started marking. I just haven't got finished. Assignment 6, which you've just handed in. And then I will get your lab notebooks with experiment 5 from TAs and I'll bring them here. So I should be returning 3 things and then receiving the formal reports. Okay, the other thing I wanted to mention is that for the final exam, you can prepare your own formula sheet. It's just a 8.5 by 11, like letter size piece of paper. And then you could write whatever you want on it, both sides. If you want to waste time by printing it in like some micro printing on some typo and you want to do all that, go ahead, I don't care. You can spend your time how you want. Okay, but that formula sheet you can bring, and then you can bring a calculator. Graphing calculators are fine. Okay, good. Any questions about that stuff? Okay. All right. So what we were talking about last time was trying to develop a bit of intuition around, or maybe intuition is not the right word, but just a better understanding of what chi-squared represents. And we went through an argument that suggested that chi-squared should be equal to the number of data points that you collect if the number of data points is really large. We then kind of went through a bit of an argument to say, well, that's not exactly right. What you actually expect is chi-squared should be equal to the number of degrees of freedom, which we denoted by this Greek symbol nu. And that number of degrees of freedom is just the number of data points that you've measured minus the number of parameters that you're extracting from the fit that you're doing. So if you're doing like a linear fit where you're going to extract a slope and an intercept, then the number of parameters m is 2. And if you measure 12 data points or something, then your degrees of freedom is 10. And that's what you would expect chi-squared to be. The rough argument is that your line that you fit through your data is artificially matched too well to those data points because we're using the data themselves to determine the slope and intercept rather than using what are the true values that we don't know. Anyways, that was the argument. So we expect chi-squared to be equal to the number of degrees of freedom. If chi-squared is bigger than that, it may be an indication that the model that you're fitting to your data is not a good model. We defined the reduced chi-squared as just chi-squared divided by this number of degrees of freedom. And in that case, a good fit, you expect the reduced chi-squared to be 1. Okay, and so that's what we spent our time on last time. One other thing that we did is we said, okay, let's imagine that we calculate chi-squared as a function of one of the parameters we're trying to fit. Like maybe this represents the intercept of a linear fit or something like that. So it has some special value that minimizes chi-squared, and that results in this chi0 squared. But then what we could do is we could imagine, well, let's start here at the minimum, and then we'll move away from that minimum, either left or right, it doesn't matter. And as we move away to some AJ prime value, then at that point, chi-squared is obviously going to be above its minimum value. We're going to move away enough until we're exactly 1 above that minimum. So chi-squared becomes chi0 squared plus 1. In that case, we said the difference, AJ prime minus AJ star, gives us an estimate of the uncertainty. So when chi-squared changes by 1 away from its minimum value, then the difference in parameters in order to see that change is an estimate of the uncertainty in the best fit value. Okay, so those are the two things we did to try to develop our understanding of what chi-squared is trying to tell us. All right, so with that, we're done our fitting stuff. I want to do one more topic, and it's kind of a fun topic because we don't really have to develop any kind of new concepts. We're just going to make use of stuff we already know to do something kind of interesting. And this will actually take us back to a little bit binomial distribution. So we'll be able to review some of that stuff. What I want to talk about is just an introduction to Monte Carlo simulations. And so this is just a very brief introduction. People make entire careers out of doing Monte Carlo simulations. And so I just want to show you kind of a basic introductions into what they're all about. Okay, so my first comment is that this is the use that we're going to do is numerical integration, but I don't want to give the impression that that's all you can do with Monte Carlo simulations. It's just a nice, gentle introduction. So this is useful for numerical integration, and it's especially useful for high dimension integrals. So imagine you had an integral where, like, you could do double integrals, right? Like a dx dy, or you could do triple integral dx dy dz kind of thing. So once you start doing these multiple integrations for functions that depend on many variables, that's when some of the stuff is really quite useful. Okay, so the Monte Carlo method uses repeated random sampling to obtain numerical results. And we'll give an example basically right now. So example 1. This is the classic example. We're going to try to use a Monte Carlo simulation to compute the value of pi. computing pi. Okay, so the way we're going to do it is we're going to imagine that we have a coordinate system with an x and a y axis, like so. And what we'll do is we'll put a square on our coordinate system, and I'm going to make my square sides of length 2. So we'll go from here to here to here to here. So this intersects the y-axis at 1 and -1, and it intersects the x-axis at +1 and -1. So the sides are length 2. And then what I want to do is inside, I want to draw a unit circle. So a unit circle is a circle with radius 1, and so it fits inside the square. And so I'll try to draw my unit circle. It looks something like this. Okay, so that'll have to do. And this circle has a radius of 1. All right, so there's the setup here. And what we're going to do is we're going to assume that we can produce numbers, random numbers that are uniformly drawn from the interval -1 to +1. Okay. Let me tell you the way they used to do this before you were born. Okay. So before computers were around, imagine you had a piece of paper that has a very uniform density. Okay. And what you do is you first cut it out to be a perfect square. And then you take that square piece of paper and you put it on a scale and you accurately measure its mass. Okay, so that's step 1. Then you draw a circle on your piece of paper and you very carefully cut out this paper so that now you have this perfect circle. And then you take the circle and you weigh its mass. So the mass of the square is going to be proportional to its area. It's just 4, right? The mass of the circle is going to be proportional to its area. So it's going to just be pi r squared, but r is 1. So the area of our circle is just pi. So then if you take the ratio of these two masses, that has to be the same ratio as the area, it's pi over 4. So what you do is you take the ratio of the masses, it's some number, that has to be equal to pi over 4. You take 4 times that ratio of masses, and that has to give you the value of pi. And so that's one way of estimating pi with some precision. Okay, now we're not going to do that exactly, but we're going to do a process that's analogous to that. Okay, so we're going to say, look, we assume that we can generate these random numbers somehow, and then we're going to repeatedly draw sample points. So xi, yi from the interval -1 to 1 by -1 to 1. So we're gonna draw 2 random numbers, and those 2 numbers are going to represent the coordinates of some point that lives inside the square. Some of those points will be in the square but outside the circle, and some of them will be in the square and in the circle. Okay. So the probability that a random point lands within the circle is I'm gonna use a funny notation for this probability of P with like a double vertical line. For some reason, I chose to do that. So it's gonna be the area of the unit circle divided by the area of R squared. And therefore, this probability is pi times R squared divided by 2 times 2 for R square. And so that's pi over 4. Okay, and so therefore, if we're trying to determine pi, it's going to be equal to 4 times this probability. And really, what we're going to do is we're going to use the Monte Carlo simulation to estimate the value of this probability so that when we multiply it by 4, we can come up with our value of pi. So we have expressed our desired quantity pi in terms of a probability P. We're going to estimate the value of P using the Monte Carlo simulation. Okay, so if we go back to this picture of the square here, what we're going to do is we're going to just keep drawing random points. Yeah. Go ahead.
What do you mean by randomly and uniformly?
I'll show you in a second. Uniform just means that there's, if I was to sample, say, 10,000 points on the interval from +1 to -1, and then I plot a histogram of those, the histogram would be flat. Like there's no preference to getting numbers close to 0 versus close to ±1. So it's just going to be a flat distribution. Yeah. So, but we'll see an example of that in a little bit. Okay, so what we're going to do is we're going to draw a bunch of points, so XY values, and some of them will land inside the circle, and some of them will land outside the circle. And we'll keep drawing these points. I'm going to draw these ones that miss the circle, and then I'll go back and put a bunch in that hit the circle. So we make these n pairs of XY values, and we populate our little plot here, and then we count how many that are inside the circle versus the total number of points. And so what would the probability of landing in the circle be equal to if I have, I don't know, X points inside the circle and a total of n points? How would you calculate this?
Over n.
Yeah, just X over n, right? So the ratio of the number of points that land inside the circle, which we're going to call a hit, to the total number of points is equal to this probability that we said was going to be pi divided by 4. Okay. So to determine the value of P, we generate n random coordinates xy. The probability that we get a point inside the circle, which I'll refer to as a hit, is well, okay, it's kind of weird, that probability is equal to the number of hits divided by the number of trials. And so I'm going to call like hit Z, Z sub n divided by n. So this is the number of hits. And this is the number of trials. Okay, and so therefore it must be the case that this probability that we could estimate as Z over n has to be equal to also pi divided by 4. And so taken all together, pi is going to be equal to 4 times the number of hits divided by the number of trials. All right. So I think what we'll do is, I'm not going to show you an implementation of this, but I'm going to show you an implementation of a similar, but perhaps more interesting problem. You know, we just did an example of essentially, I framed this as like trying to calculate pi, but we could have said that we're trying to find the area of the circle, for example. So if I know the square has area 4, the probability is the ratio of the circle area to the square area. And so I could have used that probability to determine the area of a circle. Okay, what kind of mathematical operation do you do all the time that calculates areas? Integration. Okay, so what we're going to do is we're going to recast this hit and miss problem. Instead of trying to calculate pi, let's use it to numerically integrate some function. Because integrals are in general hard to do. You know, you're given as problems integrals that you can solve all the time. But it's because your profs are feeding you problems that are solvable. The vast majority of integrals are either really hard to solve or just don't have analytical solutions at all. And so then you have to rely on numerical methods. And this is one of those methods that we can develop. Okay. So and then I'll show you an example of actually doing a numerical integration. Yeah. 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 Here, I'll start writing here. So let's do hit and miss Monte Carlo integration. All right, so let's assume that we want to evaluate the integral 0 to 1 of f of x dx, which is just equal to the area under a curve. Just going back to this example of cutting out this piece of paper. It was my supervisor when I was a graduate student that told me about this. So he was already like basically at retirement age when I started. And so, you know, he's older. So they actually did this stuff. Like they didn't have computers to do all these calculations for them. And so the example of cutting out pieces of paper wasn't to find pi, it was to evaluate integrals. So what you could imagine doing is you cut out your uniform piece of paper so that it represents your XY coordinate system. And then you draw some function you want to integrate. You draw the curve on that piece of paper. So the first thing you do is you measure the weight of the square, and then you draw on your curve. It's probably some complicated curve because you can't evaluate the integral analytically. And then you cut out the parts and you keep the piece of paper that falls below the curve. And then you weigh that, and that's proportional to the area. The ratio of those two is equal to the probability of, well, of a point landing below the curve. And so you can use that ratio to find the area of the integral. The ratio of masses is equal to the ratio of areas. It's equal to the ratio of the area under the curve divided by the area of the square, but you know the area of the square, so you can calculate the area under the curve, which is equal to the value of the integral. Another way of thinking of it, more in line with this hit and miss method, is let's imagine you put your piece of paper out in the rain and it's raining down, and you're going to just count the number of drops that hit your paper under the curve versus the total number of points that hit the paper. And that ratio is also equal to the ratio of the areas. Okay, so that's what we're going to try to do. So as an example, let's take f of x is equal to, it's some dumb function, but it's constructed in a way that's convenient for our purposes. It's a polynomial and it's a big polynomial. Minus 409,600 x to the 6 plus 3,11296 x to the 5th minus 114,688 x to the 4th plus 16384 x cubed, and that's it. Now the first thing you might notice is that why the hell would I do a numerical integration of this? It's just a polynomial. We can integrate this exactly. Well, what I want to do is I want to use a function where we can determine the exact value of the integral so that we can then go and compare that to our numerical methods and see how good we can do. Well, I'll show you why. And first of all, it's not complicated. It's just long. Yeah. So xy. The reason that this function has been chosen is because it fits inside the unit square. 1, 2, 3, 4, 1, 2, 3, 4. So here's a unit square, and that function on the interval x is 0 to 1 looks like the following. It looks like this. Let's see if we can, well, that's not too bad. It looks something like that if you plot it. Okay, so this is our f of x.
But that's only on that interval?
Only on that interval, yeah. So it could do different things past x equals 1 or on the other side of x equals 0. Yeah. Okay, so on x between 0 and 1, this function fits within the unit square. Okay, so we use the same hit and miss simulation to find the probability of a point landing beneath the curve. So our probability would be the number of hits divided by the number of trials, and that's equal to the area under the curve divided by the area of our square. And in this case, the area under our curve is the integral from 0 to 1 of f of x dx. And the area of our square is just 1 times 1. And so therefore, this integral is just equal to the number of hits divided by the number of trials. So if we were to actually implement that, what we would have is our hits will color red, and those are the points that fall underneath the curve somewhere. Okay, so these are gonna be hits. And then we're gonna have points that land in our square, but not under the curve. And so those ones are gonna be our misses. And so these are misses. Okay, and what I want to do is I want to show you an implementation of this. So I'll give people just a second to write this down. Okay. Good. Now let's see if I can share this screen. Yes. So okay. What I'm going to do is I'm going to go down to these Python tutorials. Okay, Monte Carlo hit and miss integration. Let's see if we can fire this up. So it's not there yet, but I'll put a link to this on the course website if anyone's interested in looking at it in more detail. Okay, good. So I thought we would just go through some of this together. We won't be able to do all of it, but the first thing we need to do is we need to generate random numbers with this uniform distribution. So I'll answer your question now in the next minute. So what we're going to use is this from NumPy, this random.uniform. And each time I execute this cell, I'm just going to get a random number that's between 0 and 1. So it's just some decimal number. If I execute this cell, it will, oh, sorry. Here we go. Shift enter. Right, so now it's 0.78. If I run it another time, it'll be 0.149, 0.85, and so on. So I can just keep executing the cell over and over again. I'll just get a different number between 0 and 1. You can take this random.uniform and you can specify some arguments. This argument says, give me a number between 0 and 1, and then give me 10,000 of them. And so I can say, all right, make 10,000 random numbers between 0 and 1. And so there, it's done. And then what we can do is we can plot a histogram of those random numbers. And so there it is. This histogram spans 0 to 1, and we're plotting the frequency that we got, you know, some points between maybe 1 or 0.18 and 0.2. And the number of times we got that was whatever, 220 times. But for any interval between 0 and 1, we always got about 200 events. And so that's what uniform means, that there's no preference to any particular value of the decimal number between 0 and 1. They're all equally likely. Of course, in any random trial, you're going to get some little spikes here. So we got a bit of a spike around, I don't know, maybe 0.84. But if I went and did another set of 10,000 trials, then the spike at 0.84 is gone. We get little spikes somewhere else. Yeah.
Just for, like, what would it look like if you didn't put uniform, or what was just random?
So you probably have to specify what type of distribution. Like if you did, I could ask for Gaussian distributed numbers, and I would have to say, give me Gaussian distributed numbers with a mean of mu and a standard deviation sigma. So I'd have to specify those two things. Or I could ask for Poisson distributed numbers or binomial distributed numbers or something like that. Yeah. Okay, good. So that's just random number generation. This is the exact function that we wrote down, that polynomial. And so I'll plot that polynomial here. And so that's what it looks like. It fits in the square from 0 to 1, 0 to 1. The plot's not square, but that's just because the aspect ratio is different on the x and y axes. But anyways, this curve fits in this inside a square that's 1 by 1 in size. Okay, so this next cell, all we're going to do is we're going to do an exact integration of this polynomial. So there's no simulation here. We're just getting the exact value of that integral. And sorry, I think right. So the exact value of the integral is 0.4816. So 4816, if we can remember that. All right. Is 16, what's 16 times 3? I guess that is 48, isn't it? So there you go, 48, 16. There, that's how we can remember it. All right. So we haven't done any simulation stuff. This is where we'll do the simulation, and I won't go line by line necessarily through this, but what we're going to do is we're going to generate 10,000 random points with coordinates between 0 and 1 for x and y. And then we're just going to check if that point, each of those points falls below the curve or above it. So here's the number of points, 10,000. And then this is where we generate our random numbers. So here's the x coordinate and the y coordinate. It's just inside a loop that goes 10,000 times. So we're going to generate these coordinates one by one, but we'll go over them 10,000 times. Here, we're checking, is the y coordinate less than the function evaluated at the corresponding value of x? If it is, if that's true, then that's a hit, and we're going to increase our count of hits by 1. Okay, and then I'll also write down the coordinates of the x and y values so that we could plot them later. If y is not less than the function, we'll call that a miss, and we'll increment the number of misses, and then we'll keep track of the coordinates of the misses. And then finally, the integral is equal to the number of hits divided by the number of trials, and that's all we have to do. And so I can execute this, and it's done already. So we get, for this ratio hits divided by total number of trials is 4803 instead of 4816. But of course, every time I run it, I'll get 47.5, I'll get a different value. 4839, so there's one that's a little bit above the true value. And so you just keep doing this over and over and you'll get a different value.
Will that value become more and more accurate the more like sample numbers you have?
Yes, that's right. So if I was to increase the n here, then your value gets better and better. And we're actually gonna look at that in some detail. Okay, this next block of code is nothing to do with the integration. I'm just showing you what it's done. So these are the 10,000 data points that were randomly generated, and the red ones are the hits that we counted. And so the ratio of the red points to the total number of points is the estimate of our integral. It was 0.4816, so that's roughly half, right? And it makes sense that our picture is roughly half colored red, because half the points fell below the curve. Okay, good. So you asked a question, what if we were to increase the value of n? And so what I'm gonna do here, actually, let's see. What we're gonna do is we're not gonna increase n yet. What I'm gonna do is I'm gonna calculate the value of the integral using n is 10,000, but I'm gonna do it 5,000 times. So we're gonna just run the same simulation 5,000 times. We'll get 5,000 estimates of the integral. And then I want to plot the distribution of those values. So this will take a minute. Oh, sorry, what do I want to do? Okay. So this takes a few minutes to do. We've done 0% of them, of the 5,000 trials. Let's just wait a second here. It should pop up with a 10%. There it goes. And so it's just calculating this integral 5,000 times. While it's going, I'll show you what it's going to do is we are going to, oh, right. Sorry, when it's done, it'll plot the histogram of those values, and that's what I want to show you. So I'll let this calculate, and while it's calculating, we'll do some other things, and then we'll come back to this in the last 2 minutes, let's say. Here we go. Okay, good. So your observation was a good one. It was about if I was to increase the number of trials n, does my estimate of the integral get better? And the answer is yes. So, and I can show you why, I think. So, okay, here we go. So each trial, or let's say each point that we drop onto our plot, has a probability of success P, which corresponds to a hit, and a probability of failure of 1 minus P. And so this is a miss. And so that is the exact language that we used for binomial distribution. So binomial distribution. So the average number of points landing below the function is the number of hits. And so that's just P times N. And that's what we've been talking about. I guess I've been using this probability here, so I guess we can stick with that notation. And so this is exactly what we said. This probability would be Zn divided by N. So that's pretty clear. The variance, or sigma squared, I'll put a little Zn. This is going to be the variance in the number of hits. Who remembers what was the standard deviation for the binomial distribution? Yeah, it was NPQ, remember? But Q was just the 1 minus P, the probability of a miss in this case. And so if I want to get the standard deviation, I also need to take the square root. And so therefore, the uncertainty in Zn is the square root of NP1 minus P. Okay, but what I care about is that this is proportional to the square root of N. Now that doesn't seem quite right because we would expect our uncertainty to go down as we increase the number of trials, but the square root of n increases as n increases. The problem is we haven't actually finished calculating the uncertainty in our integral. So if our integral is equal to this f of x dx, and that's equal to Zn over n, then the uncertainty in our integral is equal to 1 over n times the uncertainty in Zn, which is going to be proportional to 1 over the square root of n. Right? Because Zn is proportional to root n, so we have root n divided by n, which is 1 over the square root of n. So the uncertainty and our estimate of I decreases as 1 over root n. So if you want to cut your uncertainty down by a factor of 2, you have to do 4 times this number of trials. If you need to cut it down by a factor of 10, you need to increase your number of trials by a factor of 100. Little n is what we've been using. Okay, good. So let's go see how our little calculation is going. And so share the screen. There we go. Oh, it's finished. That's nice. Okay, so let's see. It started at 38:47 and finished at 41:29. So it took a little under 3 minutes. And here is our distribution of the number, the distribution of our estimate of the integral. You can see they all sit around 0.48, and the peak is just above 0.48. So 0.4816 is somewhere around here. And there's a distribution, and this distribution has a certain width. And so the width of that distribution tells us the uncertainty in our estimate of the integral value. And that's the square root npq, or np times 1 minus p that we did. I won't run it now because it takes too long, but I will show you something else we can do with this. Here is a little block of code. I won't read you this code, but I'll show you the one thing that it's doing. It's going to do 5,000 trials of calculating the integral, just like we did, but it's going to do it for cases where n is 100, 200, 500, 1,000, 2,000, 5,000. 10,000 is the one that we've already done before, and then we'll go up to 20,000, 50,000, and then 100,000. And so what it's going to do is it's going to calculate the width of those distributions and plot them as a function of n. And so we expect that the width of those distributions should decrease as we increase the value of n. Here's the output that you get. So here's the standard deviation as a function of n, the number of trials. When you have a small number of trials, the standard deviation is large, and it gets smaller and smaller and smaller as you increase the number. I'll make one more plot, and this plot is the exact same data, but along the x-axis, I have 1 over the square root of n instead of n. And there's the linear relationship. So out here, because this is 1 over the square root of n, these large values is small n. So at small n, we have a large standard deviation. And at low n, at large n, where 1 over square root of n is small, we have a small standard deviation. Okay, and so this is a prediction for how the standard deviation should behave, and it agrees with our calculation based on what we know about the binomial distribution. So that's our example of hit and miss. What we'll do on Wednesday next week is I'll show you one other way to do numerical integration. And it's kind of just a bit of a variation on what we've already done. Okay, good. So thank you very much. That's where we'll stop. I guess we won't see. Is anyone gonna watch the solar eclipse on Monday? Can, yeah. I don't know, is it gonna be cloudy or?
Might be, but it's
Yeah.
still like pretty far off.
Yeah. So yeah, we'll see. Hopefully, I guess in BC, it's just a small partial eclipse.
They sort of shadows them, if it is like a weird shape. Shadows, I've seen videos of that one, you got partial.
Okay, yeah.
Shadows.
Good.